As you may have guessed from the title, this video is going to cover everything you need to answer probability questions on the GRE and GMAT. But to be honest, if you're anyone interested in learning more about probability, this is going to be useful to you. I bet there is at least one thing, if not a dozen things, that you learn from this video. Just quickly, it's going to be ordered in terms of difficulty, starting with the more fundamental aspects and building up to the trickiest topics. So if you're already somewhat of an expert in probability, you can maybe skip to halfway through, or if you just want to know the basics, you can bow out at any point. And this story of probability is going to begin with two words, and or. They're essential to understand if we want to handle the fundamentals of probability. Here's the question. A raffle bag contains 7 blank tickets, 1 small prize ticket and 1 large prize ticket. Any ticket that is selected is placed back into the bag after selection. And we need to, based on this information, compare two quantities, quantity A and quantity B. Say which one's bigger, say if they're the same, or say if there's not enough information to tell. Quantity A is the probability of selecting 2 blank tickets if a total of 2 tickets are drawn at random, 2 blank tickets. Quantity B is the probability of selecting either a small prize ticket or a large prize ticket. Notice how we would describe quantity A with an and. We would say we're looking for a blank and a blank. Whereas with words, we would describe quantity B with an or. We want a small prize ticket or a large prize ticket. Now, before I give you the secret of the words and or, I want to describe the fundamentals of probability that I've written down below. A probability can be thought of as a fraction, where the numerator, the top line, is the number of ways of getting what you want, and the denominator, the bottom line, is the total number of options that are out there. So it's what you want divided by the total, not, which is what many students think and get wrong, 1 over what you want. So for example here, the chance of getting a blank ticket isn't 1 over 7. Despite the fact in the student's brain you're picking 1 blank ticket and there's 7 blank tickets available, people often say 1 out of 7. No, it's what we want. How many ways of getting what we want? Well, there are 7 blank tickets, so 7 ways of getting what we want, out of a total of how many tickets in total? 9. So the chance of getting a blank ticket is 7 out of 9, not 1 over 7, as many students would think. Well, the key thing here to notice is that the question said any ticket that is selected is placed back into the bag after selection. So the probability the next time is going to be just the same as the probability the first time. This is not a situation, which we'll cover in a second, where we're taking out a ticket and now there are fewer options available the next time. No, we're placing the ticket back in, so the probabilities always remain the same. But what about this and versus or thing that I was chatting about? Here's what you need to know. The word and basically means mathematically multiply. The word or in probability means add. So just remember that. And means times, or means add. So many students ask me halfway through a probability question, oh, do I multiply these? Do I add these? Well, just step back and ask yourself, is this a situation I would describe with an and or with an or? And the first situation, it's not like we want a blank or a blank. No, we need 2 blanks. We want a blank and a blank. And quantity B, it's not like we want small and a large. We're only picking 1 ticket. We want a small or a large. Let's quickly calculate that and see what we get. Because it's and, we're going to multiply. Now, to multiply fractions, you probably know we multiply the denominator and multiply the numerator. 7 times 7, 49. 9 times 9 is 81. So 49 over 81 is the probability of getting 2 blank tickets. Now let's do small or large. The probability of getting a small prize ticket, well, there's 1 small in total and there's 9 tickets again in total. So it's 1 over 9. Same thing with large, 1 over 9. This time it's an or, so we add, giving us 2 over 9. Now hopefully you don't need a calculator to tell that quantity A, which is more than half. How do I know it's more than half? Because 49 is more than half of 81. Quantity A is definitely going to be bigger than quantity B, which is 2/9, way less than a half. So in this case, quantity A is bigger. So at this point, many of you will be thinking, okay, Philip's explained probability and an or. How come this video is so long? Like, I've understood everything. Well, trust me, there is a lot more to learn about probability. The next thing I'm going to focus on is when we don't replace an item back into the bag, so to speak. Notice here it was somewhat easier because we placed the ticket back into the bag, and so the probability stayed the same. Well, now a Philip from a couple years ago, who you're going to see on camera, is going to explain how to deal with a situation where we don't replace elements from a bag. I'm also going to introduce the letter method, which is perfect for most of the fundamental probability questions you'll get. If there's one thing I can achieve from this video, it's to convince every single person watching to never make these two mistakes. So let's get straight to an example. What am I talking about? Imagine there was a question where it said that there are 3 red beads and 5 green beads in a bag. 2 beads are selected from the bag without replacement at random. What is the probability of getting 2 green beads? How would you do this? Let me first introduce my technique. I call it the letter technique, which is not very imaginative because it just involves using letters. But anyway, the technique involves writing down what we need in the form of letters. In this question, we need 2 green beads. That's what the question is asking for both of the beads to be green. We can use G to represent getting a green bead. So getting 2 green beads would be a G and then a G. Seems obvious, right? Seems useless, but we'll see in future examples how important that technique is. But anyway, what's the most common mistake? Well, can I just ask you, we have 3 red beads and 5 green beads. What's the probability of getting a green bead on your first selection? That's right, don't consider both selections all in one go. Can you just tell me the probability of getting a green bead on your first selection? Hopefully you said 5 out of 8. There are 5 green beads and there are 8 beads in total. So the probability on your first selection of getting a green bead is 5 out of 8. I don't want you to consider the whole scenario in one go of picking 2 beads at once. I want you to think of it as picking 1 bead and then the next bead, and we will get the right answer. Okay, so we have a 5 out of 8 chance of our first bead being green. What about that next G? What about that next bead being green? Here's the most common mistake that I see in probability. People think it's 5 out of 8 again. The problem is we've already picked a green bead out. So there's only 7 beads left in the bag. And how many of those beads left in the bag are green? 4. Because the first bead was green, there's now only 4 green beads left. So for that second G, for the getting green again the second time, we have a 4 out of 7 chance of getting a green bead, not 5 out of 8. There are only 4 greens left after we've taken the first one out and 7 beads in total. Some people remember one bit and forget the other bit. They might remember the number of green beads has gone down to 4, but they think the total is still 8. No, the total is down to 7. So it's 4 out of 7. The probability of getting the first green bead was 5 out of 8, but getting the second green bead was 4 out of 7. Getting the first one changed the probability of getting the second one. Now, what do we do with those two numbers? I touched on this in another video, but whenever the word and is involved, we multiply. Whenever the word or is involved, we add. Now, do we want a green or a green and a green? We want a green and then another green. So we do 5 out of 8 multiplied by 4 out of 7. The and means multiply. You could simplify those fractions or multiply them straight away to get 20 over 56, which simplifies down to 10 over 28 or 5 over 14, which is our correct answer. 5 over 14 is the probability of us getting 2 green beads from our bag. So far you're thinking, okay, that makes sense, that's really good, Philip, but that letter technique wasn't really useful. When is it useful? The next 2 examples will show more and more why it's essential, especially the last example. Okay, so what's our second example? Imagine we have the same scenario with the 5 green beads and the 3 red beads, except this time the question was, what is the probability of picking 2 beads of the same color? Now, with letters, can you write out the 2 scenarios in which we end up with 2 beads of the same color? Hopefully you got R and R standing for red and then red, or G and G standing for green and then green. Let's work out those 2 scenarios. First, R and R. Can you tell me the probability of getting red and then red? The first red would be 3 out of 8, and the second red would be 2 out of 7, as we saw earlier. 3 out of 8 times 2 over 7 is of course 6 over 56. But this time I don't want you to simplify. In the harder probability questions, save the simplifying until the very end, and you'll see why in a moment. Now, we don't need to work out the probability of getting a green and then a green because we already did it with our previous question. It was 20 over 56, which we simplified, but we're not going to simplify it here. 20 over 56. Now here's the key question. Do we add those 2 together, the red and red, green and green, or do we multiply them? Do we add the 6 over 56 to the 20 over 56, or do we multiply? Well, we want a red and a red or a green and a green. You can't have a red and a red and a green and a green because that'd be picking 4 beads. We're just picking 2. It's red and red or green and green. 2 beads of the same color red or 2 beads of the same color green. It's an or, so we add. And that explains why we don't simplify, because now we have a simple addition to do. 6 over 56 plus 20 over 56, which gives us 26 over 56. And only now, at the last stage, do we simplify. 26 over 56 divides by 2 to get 13 over 28, which is our correct answer for this second question. I know what you're thinking, we still haven't gotten to the second most common mistake, but that's going to come up in this, our third and final example. Imagine again we have the same scenario, except this time the question was, we're picking 2 beads at random and without replacement. What is the probability that the 2 beads we pick have different colors? This example ties in everything I've been talking about. Most students at this point would say something like 5 out of 8 times 3 out of 7. They'd say, look, there's 2 beads of different colors, a green bead and then a red bead. And they would show off and say, look, I remembered that the total number of beads goes down to 7. But that answer would be wrong. Why is it? Well, one reason I can give is they didn't use the letter technique. With letters, can you show me how to get 2 beads of different colors? Hopefully you wrote down G and then R, and you wrote down R and then G. And that's why I recommend using letters. It's much more obvious that we have to consider both scenarios. G then R, R then G. If we just focused on G then R, which is 5 over 8 times 3 over 7, we're working out the probability of specifically getting a green first and then a red. But that's too narrow and too specific. It could have also been a red and then a green, and we have to account for that fact. Using letters reminds us to account for all the different orders in which the question could get the desired result. And that was the second most common mistake in all of probability, neglecting the different orders in which things can happen. Just considering G then R and not considering R then G. We have to consider both to get the right answer. Let's work out G and then R. That's 5 out of 8
times 3 out of 7. The second fraction is 3 out of 7 because after we've picked the green bead the first time, there are still 3 red beads, except there are only 7 beads in total. That multiplies to get 15 over 56, which again, we do not simplify until the very end. What about getting a red and then a green? Can you work that one out for me? You can even pause the video and try and work out the whole rest of the question if you like. A red and then a green would be 3 over 8 times 5 over 7, which gets us 15 over 56. Do we multiply those probabilities or do we add them? It's a green and then a red or a red and then a green. So we add 15 over 56 to 15 over 56, giving us 30 over 56, which we can simplify down to 15 over 28 and no further. We have our final answer of 15 over 28 for the probability of picking 2 beads of different colours. And that demonstrated how to avoid the second most common mistake in all of probability, neglecting to consider the different orders involved. So now in one short video, you've seen the 2 most common mistakes in all of probability. Not adjusting for when you've already taken out a certain bead and reducing the total and the numerator, and 2, neglecting the different orders. You've also seen how I use letters to represent possibilities to make my calculations easier and clearer.
If you've followed so far, you've already learned, I would say, 40 to 50% of the kind of questions that you'll be tested on in an exam like the GRE. But keep going, there's much more to learn. Notice one thing I didn't cover in that video with those letters is a specific order. Specifically red then green, for example. And I want to talk about what we do when they ask about a specific order. And at the bottom, I've put the quote, "and then" is usually the phrase they'll use when we're dealing with a specific order. What would the question look like? Let's read it. 8 candidates are waiting to be interviewed, of which 3 are wearing ties and 5 are not. If the order in which these candidates are interviewed is random, what is the probability that, for the next 2 interviews, a tie-wearing candidate and then a non-tie-wearing candidate is chosen? So they want a specific order. Tie and then not tie. Notice they could have phrased it very differently. They could have just said, what's the probability for the next 2 interviews that we get 1 tie-wearing candidate and 1 non-tie-wearing candidate? Well there, because they didn't use the phrase "and then," the order wouldn't matter. But here the phrasing is different. They want a specific order. They want the tie person first and then the non-tie person. How do we cope with that? Well, we would write T, then N, if we're using the letter method, but not NT. We only need the T and then the N, not NT, because we're going to do tie first specifically and then not tie, not the other way around. So just one letter combination here, tie and then not tie. Probability of the next person being a tie-wearing person would be 3 out of 8. There's 3 of them out of a total of 8, not 1 out of 3, for example. And is multiply, and then not tie. Now, there was no mention of the person who's being interviewed going back out and waiting again. So this is not a replacement situation. This is a without replacement situation. So the total number of candidates has dropped to 7, of which 5 don't wear ties. And again, and means multiply. So we'd multiply these 2 fractions to give us 15 over 56. And I really think that was worth pointing out, how when you have the phrase "and then," we want a specific order. So we only use one of the letter combinations, which is very different from if they just said we want 1 tie-wearing person, 1 non, in which case we'd also do NT as well as TN. Okay, things are about to get even more exciting. What about a question like this? Philip is one of 9 employees eligible for a field trip. If 4 places are to be assigned randomly, what is the probability Philip is among those assigned to the field trip? Now this is kind of cruel because I asked this question straight after I taught you about letters, but we really don't need the letter method here. This is literally just, and many of you would have gotten this straight away, Well, given that there are 4 places available out of 9 employees, the chances of Philip being one of those is 4 out of 9. And I just wanted to point out, when you're one of many in a situation like this, you don't need to overcomplicate with thinking about every single scenario. You don't need to think about, well, he could be the first person assigned, which is 1 out of 9, or he could be the second person assigned, which means he wasn't one of the first, so that's 8 out of 9, and then was the second, 1 out of 8, and then the third person, and then the fourth person, and then add it all up. That would get you the same answer, by the way. This maths is completely legitimate. You would get 4 out of 9. I just thought it was worth pointing out, in this simple scenario, when there's just 4 slots available, and Philip is one of the 9 just randomly chosen, well, his chances are just 4 out of 9. It is that simple. Now, if you're curious about this method of picking one by one, that will be useful. Right towards the end of the video, we're going to cover a tough question where you do need to consider the order in which they're picked. But for now, when you're just one of many, yes, I can reassure you it is just that simple. Just pick the number of people out of the total, and that's Philip's probability, just like anyone else's. And in case you're wondering, if there was a second person, say Philip and Christina are going to be picked, it would be, well, Philip's chances are 4 out of 9. And given that Philip has now been picked, Christina's chances are 3 out of 8. Only 3 slots left out of 8 people. It is that simple. We don't need to think about all the different letter arrangements. It's just this simple. Right, now we're going to cover questions where the topic is disguised. And I'm going to mix in a few of these throughout the remainder of the video. What I mean by disguised questions is they're asked as a probability question. And if a student was asking me, they'd say, I got stuck on probability, when really it wasn't a probability question. It was a ratio question, or maybe a Venn diagram question, or a combinatorics question. And even though the student might call it a probability question because the test uses the word probability, it's actually one of those other topics. So I wanted to give you a few examples of those. This is a disguised ratio question. Let me explain. Adults and children are at a party in the ratio 3 to 5. If a person is picked at random, what is the probability that they are not adult? In other words, what's the probability that they're children? Now, I know that seems like a probability question because it's got the word probability, but really it's not. It's more like a ratio question. You need to know, and I've done a video on ratios, that you can convert ratios into fractions by adding them up. So 3 and 5, you write down the ratio, you add up 3 plus 5. That gives you 8. Now you can convert both sides into fractions. So adults are 3/8 of the total. Children are 5/8 of the total. So really you need to know ratios to get this right. Therefore, the question is, what's the probability that they're children? Well, 5/8. Just like we talked about just before, it's just the number over the total, 5/8. The answer is not going to be 3 out of 5 or something. So to get this one right, we need to know a bit of ratios. It's more of a ratio question than probability. But anyway, now things are going to get noticeably harder for the last part of the video. I'm now expecting most students to get these kind of questions wrong from here on out. So feel free with any of these explainer topics to pause the video, try them yourself, and see if you get them right. Because the next 2 questions are going to be about calculating opposites. What do I mean by that? Here's the question. On any given day, the probability of it snowing in Mountainville is 1/4. Nice. What is the probability in any given 4-day period that Mountainville experiences snow? Now, if you've been following so far, you'd know that I recommend the letter method. But you may be thinking, wow, if we call snow S and we call not snowing N, there is a lot of ways to experience snow. And I want you to know that if you're thinking that, or you tried that when the video was paused, you're absolutely right. There are far too many letter combinations to write down. Well, actually, not far too many because I'm about to write them down, but it's not the most efficient way of doing it. So what's the alternative? Let me demonstrate. We're still going to use the letter method. So S for snow, which is 1/4, N for no snow, which is going to be 3/4. Something happening and not happening always has to add up to 1. Okay, so snow 1/4, no snow 3/4. What we're going to do is simply work out the opposite. Instead of calculating the probability and all the different combinations of getting snow, we're going to calculate the ways of not getting snow, which with letters would simply be no snow, no snow, no snow, and no snow. N, 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 N. That's far easier to work out than look at all of that. All of those combinations where snow appears. I'm not going to read them all out, but SNNN or NSNN, etc., etc. So many combinations. And that's what you'd have to work out if you just literally worked out what they asked for, which is experiencing any snow. Far easier often to calculate the opposite, which in this case is experiencing no snow, 4 N's, and then take away from 1. I'll show you that in a second. Both ways, by the way, if you did calculate all those, 10, 20 scenarios, you would get the right answer if you add them all up. But I'm saying it's far quicker to work out the N scenario. So in this case, no snow is 3/4, and it's an and, so we're multiplying, giving us 81 over 256. Now, as you may have noticed, that is the probability of not getting snow when the question was actually asking for experiencing some snow. So we find out what's left over from 1. And the way to think about that, if you're doing 1, take away that, is just how do we get from the numerator to the denominator? What's left over to get from 81 to 256? It's 175. So that's the answer. 175 over 256 is the probability of getting any snow, whether it's on 1 day or 2 days, 3 days, or all 4 days. So think opposites. It's not always the best way of doing it, but often it is. Here's another example of a similar idea. Siobhan, that's how you pronounce it by the way, I think it's an Irish heritage name or Gaelic. Siobhan tosses 5 coins. What is the probability that at least 2 of the coins land on heads? Now here, calculating the opposite is still the best idea. It's not super simple like it was in the previous question, but it's still better than the alternative. What do I mean? Getting at least 2 heads could be done by getting 2 heads, 3 heads, 4 heads, or 5 heads. Whereas the opposite, not getting at least 2 heads, would be getting 1 head or 0 heads. And notice that latter scenario sounded a lot shorter than the former first scenario. Let me demonstrate. Heads, we're going to call H, of course, a half. Tails, T, a half. And it is easier to work out the opposite, not getting at least 2. Remember the phrase at least. It's a very important phrase to notice. I have done another video on this that you can check out. But the phrase at least is very important to notice. At least 2 means 2 or more. So the opposite of 2 or more is 1 or less. So notice these 6 scenarios are all 1 or fewer heads. First one's all T's, 0 heads, and the next 5 are just a single head. Now I'm going to take a few moments just to give you a little whispered update, just in case some students are wondering, could we have used combinatorics? We are going to get to a combinatorics example in a second, but you're right, we can use combinatorics, 5 choose 1, to work out that there were 5 ways of getting 1 head. But if that's a bit complicated sounding for you at the moment, you're not too confident on combinatorics, you can just, using letters, write out all the different scenarios manually. Notice how I've started with the H on the left and then gradually moved it across to the right, just to make sure I haven't missed any of the scenarios. And can you see that there are 6 scenarios in total? And it's much easier to do that than there are 26 other combinations where we get 2 heads, 3 heads, 4 heads, or 5 heads. I definitely should have written or 5 heads at the end because we'd add up those scenarios, which find the probability of getting 2 heads and then add the probability of getting 3 heads, add 4 heads, and add 5 heads. But that's 26 combinations, whereas this, our original method, is only 6 combinations. But let's just finish it off though, because 6 combinations is still fairly tricky. All 5 of them being tails would be a half times a half times a half, because that's and, giving us 1 over 32. And the good news is, because it balances out perfectly, with a head being the same probability of the tails, all those 6 combinations are also going to have a 1 over 32 chance of happening. So we simply do 1 over 32 plus 1 over 32 6 times, or just 1 over 32 times 6. The reason I wrote it out in full is just to show you that technically what we're doing is adding each of those. It could be 5 tails, or a head at the start, or a head second, etc. So we're adding those, giving us 6 over 32. That's the probability of not getting at least 2 heads. Therefore, as before, we do 1 take away that answer. So how do we get from 6 to 32? We'd have to add 26. And so the answer is 26 over 32, which simplifies to 13 over 16. That's the probability of getting at least 2 heads. We are getting to quite a high level now, so do at any point feel free to pause and re-watch certain sections. But don't give up if you're finding it hard, because I have lots more juicy tricks to come to finish off the video, all of which could come up in the GRE and GMAT. For example, disguised Venn diagrams. Now, I've done separate videos on Venn diagrams I urge you to check out. It's later on in my week 5 playlist that you can find on my channel. But I just want to show you how they can disguise a Venn diagram question as a probability question. Let's see. The probability of event A occurring is 40%. The probability of event B occurring is 50%. If the probability of both event A and event B occurring is 30%, what is the probability of exactly one of the events occurring? Well, it definitely seems like a probability question, right? I can see the word probability like at least 3 or 4 times. But in a way, it's actually just a Venn diagram question. How do I know it's a Venn diagram question? Because we've got the word both. Anytime I see the word both or neither, I'm thinking Venn diagram. So how would I draw a Venn diagram here? Well, we draw one bubble with event A on top, and another overlapping bubble with event B on top, and we draw a box around. This is the essential way of doing a Venn diagram question. If you want more practice on this, as I said, do check out my Venn diagram videos. Now, the probability of event A occurring is 40%, they told us. So we put that on top of the bubble, definitely not inside. If we put it inside, we're saying that's the probability of event A, but not event B occurring is 40%. No, they said just in general, in total, event A is 40%, so it goes on top. Event B was 50%. The probability of both, I think you can guess where that goes, is 30%. Now, do you notice how with the Venn diagram, we can now calculate all the remaining sectors of the Venn diagram? You see how the event A bubble is 40% in total, and yet 30% of it is already accounted for in the middle. So that leaves only 10% left over for the left. That 10%, by the way, is the probability of event A only occurring, not event B. Likewise, for the event B bubble, we know the total is 50%, 30% is already used up in the middle, leaving 20% left over. Now, I know the question didn't ask this, but just to show off how good a Venn diagram is, we can now instantly calculate the outside bit. That's the probability of neither event A nor event B. Given that the total box has to add up to 100% when we're dealing with percentages, we simply add up everything in the middle, 10 plus 30 plus 20, which gives us 60. And what's left over from 100%? If we've used up 60, 40. So the probability of neither event A nor B occurring is 40%. Now, what's the actual question? What is the probability of exactly one of the events occurring? They just want one of the events occurring, not neither of them, not both of them, just exactly one of them. So that would be the 10% plus the 20%. I know some students get confused with the wording here and they think, do they mean exactly one being event A or exactly one being event B? They mean just a total of 1. So it could be event A only or event B only. So 10% plus 20%, which of course gives 30% answer C. Now, it did seem like a probability question, but I would far more describe this as a Venn diagram question. And just to be super clear, when you finish this video, you're going to know everything about probability, but of course they can disguise a prime numbers question as a probability question. They can disguise a percentage question as a probability question. So there's no guarantee that you're going to get every probability question right, because of course you may need to know quite a lot about the other topics too. But at least in terms of probability, you'll be sorted. Okay, next topic, getting really pretty interesting and hard now. This word independent, crops up occasionally, and the vast majority of my students don't know what it really means. The question is, the probability of event P occurring is 0.3. The probability of event Q occurring is 0.4. If events P and Q are independent, what is the probability of event P occurring but not event Q? The key thing you need to realize is that the word independent means you can multiply the probability of each one occurring to get the probability of both. In other words, if you see the word independent, you multiply the probabilities of each to find the probability of both. To some of you, this may come as something of a shock because you may already have thought you can just multiply two probabilities to get the probability of both. But no, technically you can only do that if they say that they're independent or if the context is very clear that they're independent. For example, tossing dice or tossing coins. In that case, they're clearly independent, so the probability of getting both a head and a head is a half times a half. But with situations like events or any other type of probability, they need to explicitly tell you they're independent for you to realize that you multiply to get the probability of both. If you're wondering why that is, it's because in real life, two events might not necessarily be independent. One thing might affect another thing. For example, I could say to you, the probability of a certain politician being elected is a quarter, and the probability of taxes going up is a quarter. And it would be incorrect for you to then say, okay, well, the probability of that politician being elected and taxes going up is a quarter times a quarter, 1/16. No, because maybe it's the politician who's going to raise the tax. So actually the probability of both of them happening is a quarter, because the moment that politician comes in, taxes will definitely go up. So you see how it does matter if two events are linked or if they're independent. But the thing you really need to focus on for the GRE and GMAT is if they use that specific phrase independent, it means you're allowed to multiply the two of them to get the probability of both. In this case, event P, 0.3 times event Q, 0.4, giving us 0.12. That's the probability of both. With that knowledge, we can now easily answer the question. They want event P, but not event Q. Well, event P is 0.3. And of that, we know 0.12 is both of them happening. So we can simply subtract. If that doesn't make sense, draw out a Venn diagram and give the total of the P bubble 30% or 0.3. And then the overlapping bit is 0.12 or 12%. You can see clearly from the Venn diagram that what's left over on the left inside event P but not inside event Q is going to be 30% take away 12%, which is 18%. That's P occurring but not overlapping with event Q not occurring. But how do we get that? By knowing about that word independent. So it's a great one to know. I'm now going to teach you about a somewhat interesting and strange probability scenario in which sometimes the first choice doesn't even matter. Let me describe it. There is a type of probability question that I always see students fall for. Now, I've only got two questions because it's a fairly simple trick, but with this question that you can see on screen, feel free to pause the video, try it yourself to see if you get it right. And then if you don't, you can see my method. But even if you do, the next question following it is going to be even harder. If you get them both right, then well done. You are definitely on your way towards a mastery of probability. Let's look at this trick first and this question. There are 10 pairs of gloves in a drawer, and each pair is a different color. If Lolu picks two gloves at random from the drawer, what is the probability that they are not the same color? Now, what you probably already know is that we have a choice in probability. We can either work out the thing that they're asking or work out the opposite of what they're asking. We decide, is it easier to work out one or the other? In this case, it might be easier to work out the probability that the two gloves are the same color. That strikes me as being easier than working out the probability that they are different colors. Of course, once we've worked out the probability that they're the same color, then we can do 1 minus that answer to get the probability that they are not the same colour. Always bear that option in mind when you're doing probability questions, that you can choose to find directly the probability they're asking for, or the opposite of what they're asking for and do 1 minus result. Either way, let's get to the actual trick though. How do we find the probability that they are the same colour? And this is where so many students would get stuck. They would say to themselves, okay, we've got 10 pairs of gloves. That means that there are 20 gloves in the drawer. But they're 10 pairs, right? So 10 different colours, 2 gloves each. And they're thinking, but what colour am I aiming for? We want 2 of the same colour. Well, I guess let's just say red is one of the colours. So we've got a 2 out of 20 chance of getting a red glove, and then maybe a 1 out of something chance of getting the next red glove. Then it gets an answer way smaller than these. And then students get really confused, basically. They're not sure what to do. Well, here's the trick. Sometimes the first choice is no choice at all. If we want to pick out 2 gloves of the same colour, we're going to have to think about this glove by glove. And let's focus on that first glove choice. I know it says she picks 2 gloves, but we are allowed to, and I encourage you to, think about that as one choice followed by another choice. So on that first choice, does it matter what glove she picks? This is the heart of the trick that I'm trying to tell you. She's going to pick out 2 gloves and we're going to do it one by one. And when she picks out that first glove, if we're aiming for 2 gloves of the same colour, does it actually matter what colour the glove is on that first choice? No, because we're not aiming for a particular colour. We're not aiming for 2 red gloves or 2 green gloves. We're just aiming for 2 gloves of the same colour. So on that first choice, she actually has a 20 out of 20 chance, a guaranteed chance, that she picks an appropriate glove, because we actually don't care what she picks the first time. She could pick a red one, a green one, it doesn't matter. It's the second choice where we want the glove to be the same colour. The first choice doesn't matter, and that's why I call this the unexpected probability trick. Out of the 20 gloves available, she can pick any of the 20 for her first choice, and that's why we have 20 out of 20. But once she has chosen that first glove, now we have to think about, for her second choice, what's the probability that she picks a glove of the same colour as the one she's already chosen? So now it's not 20 out of 20. There are 19 gloves only left in the drawer, and she has to pick, if we're aiming for the same colour, the exact same colour as the one she already picked. So what's the probability? It would be 1 out of 19. The 19 because we've already taken 1 glove out, so there's only 19 gloves in total left. And the 1 because it has to be the one matching glove to the one we've already picked out. So say that she picked out a blue glove the first time, it would have to be the one remaining blue glove the second time. It can't be any other colour. Of course, with probability, we're going to multiply because she has the first choice and the second choice, so we multiply. And 20 out of 20, funnily enough, is just 1. Anytime the numerator and denominator are the same, that's just 1. So it's 1 times 1 out of 19, which is 1 out of 19. And we have ascertained that the probability she picks 2 gloves of the same colour is 1 out of 19, which is really freaky, but it makes it quite easy now to see that the probability that they are not the same colour would be 1 minus that, which is 18 out of 19. So that's the lesson in a nutshell. Think about things choice by choice and decide what we are allowed for the first choice and what we are or are not allowed for the second choice. Don't try and scramble them together or think of them as a group. Just sit back and think about your first choice and think about what's allowed. If we want 2 gloves of the same colour, any out of the 20 will be allowed for that first choice. Now it's going to be different numbers for the next question and a different scenario, but I want you to use that same approach where you don't try and lump things together. Just sit back, relax, think about the first choice, decide how many options you have. Then once you've made that choice, think about how many remaining options you have for the second choice. As before, feel free to pause the video and answer this question yourself before you see my explanation. And for the GMAT, I would estimate this is a 700 plus level question. For the GRE, somewhere between a 165 to 170 level question. There are 12 children in one class and 25 children in another class. There are 3 pairs of twins split between the classes, with 3 of the children in the smaller class each having a twin in the larger class. If 2 children are selected at random, 1 from each class, what is the probability that they are sibling twins? Okay, so one choice at a time, as I've written down below. Let's focus on our first choice from that first class. How many of those 12 children, and we're going to pick one of them, are we allowed to pick if we're aiming for sibling twins between the 2 classes? The answer would be 3 out of 12, because we're not looking for a particular pair of twins, so that would be 1 out of 12. We're looking for any sibling twins. So for that first class, obviously we can't pick one of the 9 children that don't have a twin, but we can pick any of the 3 that do have a twin in the other class. So that would be 3 out of 12, which is of course 1/4. What about our next choice? Once we've picked that child, one of those 3 children from the first class, moving on to the next class, what's the probability that we now get a twin for the second class? The answer wouldn't be 3 out of 25, it would be 1 out of 25, because we need the sibling twin of the child we already picked from the first class. This is not like a whole new question that just starts off at the second class. You have to take account of the fact you've already picked out a child from the first class. And once you've picked out a child from the first class, you then have to get that specific child's twin in the second class. So yes, for your first choice, it doesn't matter which of the twins you pick. So when we went to that first class, the 12 children, and we walked into that room, we could pick any of those 3 kids that had a twin in the other class. That's fine. We didn't care whether it was one of them or the other, as long as it was one of those 3 kids that had a twin. But once we've picked that kid, held their hand and moved them out of the room, and we walked towards the other class, we now need to get that twin's sibling twin for the other class. So there's only 1 child in the larger class of 25 who's the sibling twin of the child we've already picked. So that's 1 out of 25. You've got to think one choice at a time, taking into account the choices you've already made. It's a bit like life. And as before with probability, we multiply these, and if you multiply those, 1/4 times 1 out of 25 is 1 out of 100, which is 1%. These are understandably tricky probability questions, and if you're not trained in them, they're very easy to get wrong. So don't blame yourself if you didn't get these questions, but now you've seen the trick and these kind of questions aren't so unexpected to you anymore. I really hope it comes up in the test now for you so that you can get yet another question type correct. Now, I promised much earlier on in the video, if you remember, it's when we was talking about Philip and Christina being picked among 9 candidates, that sometimes the order matters and there'll be a situation where we have to keep trying until we get something. This is a rarer question type, but a really fun one to cover and learn about. Let's show you an example. Jeff plays a game that always gives him a 40% chance of success each turn. Jeff decides to stop playing only when he has a successful turn. He's going to keep going until he gets success. What is the probability that Jeff stops playing on either his second or third turn to the nearest integer? Now, many students would just think, well, it's 40% the first time, 40% the second time, 40 plus 40, 80% chance by the second turn. But then they might think to themselves, hang on a second, third term would be another 40%, that's 120%. Hang on, that doesn't make sense. Then they get confused and give up. You can honestly type in the comments if that's what happened to you. Now, if that doesn't work, what does work? What is the correct way? Well, you're certainly right that the first turn, there's a 40% chance of success. I'm going to call that 0.4. But for him to get success on the second turn means that he must have necessarily not gotten success on the first turn. And many students ignore that bit. They forget that for him to be successful on the second term, Jeff must have been unsuccessful on the first term. So he must have had 0.6 times 0.4. The 0.6 is him failing on the first term, and then, and means multiply, and then getting success on the second term, 0.4. Multiplying those, you get 0.24. So the probability drops dramatically. So it's 24% chance he stops on his second turn. What about the third turn? You may wish to pause and work this one out yourself, but it would be failure on the first term, 0.6, failure on the second term, 0.6, and then success on the third turn, 0.4. Multiplying those gives you 0.144. And now we can simply add these results depending on what they want. Do they want success on the second turn only, or on any three of the first turns? No, they wanted success specifically on either his second or third turn. Or is add, so we add the 24 and the 14.4, so that's 24% plus 14.4%, giving us as a decimal 0.384, or as a percentage 38.4%. To the nearest integer, that is of course b. And I'll confess these are probably my favourite type of probability questions, where you keep going until a certain thing has occurred.